Hello and welcome to today's IWCS webinar. My name is Connie and I'll be the WebEx producer for today's event. Now I am pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after this presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Jose Castro, manager of the Fiber Research Group, Panduit Corporation in Illinois, USA, who will be presenting his paper on impact of DMD tilt on BiDi multimode multi-wavelength transmission performance. Dr. Jose Castro is currently the manager of the Fiber Research Group in Panduit. He received his PhD in electrical engineering from the University of Arizona in Tucson in 2006. Jose was the editor of Fiber Channel T11.2, Physical Interfaces Standard for 64G transmission. He is currently working for the next fiber interface for 256G. Last year, he was a recipient of the Technical Excellence Award from the International Committee for Information Technology Standards. Dr. Castro authored over 70 technical articles and international conference papers in areas of multimode fibers, optical communication, integrated optics, imaging systems, and LAN copper cables. He has made multiple contributions to TIA, IEEE, and fiber channel standards in topics related to fiber and VCSELs. He is also a co-author of the book in holographic applications in solar energy conversion processes and holds over 20 patents. Jose, we welcome you to present at today's IWCS webinar series event.
Thank you, Ed, for introduction. Good morning, good afternoon to all the attendants. Before going to the main topic, I would like to talk about the reasons because my research group invests some time to investigate this phenomenon of the DMD tilt. As many of the attendants know, there is a significant growth in data traffic. In 2016, we reached a zettabyte of IP traffic, and of course, that means 3 or 4 times more traffic inside data centers. In the majority of data centers, enterprise data centers, multimode fiber have been predominant because of the lower cost of the transceivers and the resilient, because the fiber is more resilient to contamination or misalignment. However, trying to go faster and faster over multimode fiber becomes challenging because of the modal and chromatic dispersion of the fiber, and also the limited response, frequency response of the lasers used in multimode fiber transmitters. As I'm talking now, many companies, including Panduit, are working to develop the new standard for transmitting 100 gigabits per wavelength for multimode fiber. My research group is going to present next week in IEEE about one of the first experimental results for that. So for that, it becomes very, very important to understand the limitations of Panduit and multimode fiber. Well, let's start with the topic of multimode fiber. Multimode fiber modal bandwidth has been investigated for many decades there is so many interesting work performed during the 80s for many groups, especially at that time from Bell Labs. What the theory says basically is, of course, that the bandwidth of the fiber depends on the modal and chromatic dispersion of the fiber. And the modal dispersion of the fiber depends on one parameter of the fiber that is called the refractive index profile that is being shown in this slide. The refractive index profile can be represented by the equation showing here, where the alpha parameter tends to be a number very close to 2. However, a small variation of this value from the optimum value produces high variation from the dispersion of the fiber. Ideally, the fiber should follow this profile as shown here. In practice, we have measured a refractive index of many fibers from major suppliers. Here I'm showing 4 of them, 4 major manufacturers of fiber, in which you can notice that it's very difficult to follow exactly the alpha profile. There is always some defect in different regions of the fiber, and sometimes around the center, and therefore they produce significant impact in the differential mode delay. Sometimes there is changes on the ideal alpha profile because of the design of the fiber too. Now, most of the multimode fiber are bending sensitive, or all the multimode fibers right now are bending sensitive. So they use some trenches in the cladding area to confine the light inside the core of the fiber. So for many reasons, it's very difficult to maintain the ideal alpha profile refractive index of the fiber, and that has impact on the modal bandwidth. Today, we have different categories of multimode fiber. The ones that are being used for higher speed or gigabit speed are usually OM3, OM4, and more recently, there is the OM5 fiber that basically has the same bandwidth of OM4, but has a better response at longer wavelengths. Because of all these manufacturing variations, it's very important to test the fiber, the manufactured fiber, to grade, to estimate what is the bandwidth of the fiber. A standard test that has been used for many years is the differential mode delay. This test is defined in the TIA and IEC standards, and basically consists in sending launching a very narrow pulse inside the core of the multimode fiber at different positions inside the core. The pulse width of the probe laser is usually between 14 or 20 picoseconds, so it's very, very narrow pulse. And the pulses, after propagating through the fiber, are captured by a very fast detector and a scope, and at different radius positions, they produce a shape like the one I'm showing, and this is what we call DMD profile. Those are DMD pulses that travel at different, that were launched at different positions inside the core, travel through the fiber, and get distorted. So they travel at different speeds, and also they get distorted because of the fiber. This DMD profile is basically the main parameter that will define the bandwidth of the modal bandwidth of the fiber. Ideally, we would like all the pulses inside the core travel at the same speed, so they will be aligned perfectly, as you can see here. But in practice, because of the manufacturer or design difference from the ideal alpha profile, you get a DMD profile like this. Depending how different are the speed of the DMD pulses, you might get a OM3, OM4, or even OM2 fiber. So again, this is a well-defined test in the standard. But what we want to talk, or I want to talk today, is an additional parameter that was not considered in the standard, at least the standard defined originals for estimating the bandwidth of the fiber. What I'm talking is the DMD tilt. So it's kind of easy to imagine that if you imagine that the pulses, DMD pulses have very different speeds, you will produce a broadening of the pulses that transmit the data from the transceiver, and you will produce inter-receiver interference. So many people understand that the more different are the pulses, the speed of the pulses or the delay of the pulses, most likely you will produce inter-receiver interference. What's difficult to explain in events or even in the standards is why the sign of the tilt is important. Because if you think about this, it doesn't matter from what direction you measure height, right? From foot to head or head to foot, it's the same value. It doesn't matter the sign of that. Many people thought in the beginning that as long as the pulses they have similar slope, these two fibers can have similar bandwidth. It doesn't matter what is the sign of the slope. What I'm going to demonstrate in this presentation is that the sign is very important, especially for modal bandwidth, for two factors. One is the actual bandwidth at 850 nanometers, and the other is the bandwidth at longer wavelengths. So let me explain a little bit more what is DMD pulses represent. So this number, 0 here, represents the center of the core. Again, we're talking about a multimode fiber that has 50 microns diameter. So usually we measure the DMD or the distortion of the pulses from the center at 0 here in this axis to the end, 25 microns at the end of the fiber. In two fibers can have the same tilt or similar bandwidth, but one of them can tilt to the left and one to the right. What is the physical meaning of this? The physical meaning is that the one that tilts to the left, the higher order modes propagate faster than the lower order mode. The difference between these can be similar, but these propagate faster. In case of the right tilted fiber, the higher order modes represented by higher radial offsets here travel faster than the lower order, slower than the lower order modes represented here. So that I'm going to show in the next slide why is this so important in the final bandwidth of the multimode fiber. So as I mentioned, this sign of the DMD tilt will have two effects. One is at 850 nanometers, which is the wavelength or the spectral window we use most commonly right now for transmitting data. And the other is the effect of longer wavelengths, talking about 900, 920, or even 940 nanometers. Just as a reference, a solution 100 gig BiDi, that means bidirectional, use 850 nanometer wavelength in one channel, one direction, and around 910 in the other direction. So, okay, let's focus first why the DMD is important. In order to do that, we need to understand that the lasers used in multimode fiber are less expensive lasers, are manufactured in a wafer and tested at the same time, for that reason are less expensive, and have different geometry than the lasers used in single mode systems. Lasers used in multimode fiber have a wider cavity in a direction perpendicular to the propagation of the light. Because of that, they have several transversal modes, so the laser is by itself is multimode. Each mode is associated with different wavelength of frequency, resonant frequency. What's the meaning of this? That at the end, you can imagine that the light launches like a series of rays. Each ray has different colors, like a rainbow, has different frequencies. And from the side of the multimode fiber, we can also think that the modes can be represented by angles. So now if you couple modes from the VCSEL to modes from the fiber, and imagine that, again, the simplification that there are angles, then you will see that each mode of the fiber will be receiving different color of the laser. So then the phenomenon of a modal and chromatic dispersion become more complex because there is immediately you can see an interaction between modal and chromatic dispersion. You can derive this from the theory of the VCSELs, but in our laboratory we also have measured that. We presented these results last year, a couple of years ago in the standards. Those are actually measurements what I am talking about. This is the rainbow that I'm talking about. So those are images captured from the core. This is the core of the multimode fiber, measured every couple of microns using a scanner and connected to the optical spectrum analyzer. So what you see here is color. It's not really intensity. The red one represents a longer wavelength, as you can see here, A49.7, and the bluish color represents a shorter wavelength. So what I was saying in previous slide is like the coupling of the modes from the VCSEL to the modes of the multimode fiber are spectral dependent. So longer wavelengths tend to couple more to the lower order modes of the fiber. And you can see here that's happening for different solutions for 100 gig, SR4s, and BiDi. Again, this is a tendency. This is a physical phenomenon, so it was not designed to happen in that way. That's the reason many experts in the standard didn't know or neglect this effect in the past. So that happened just because the VCSEL resonates and have modes like a fiber, and each mode has different wavelength and frequency. And this is a tendency. So it's not a perfect rainbow, as you can see here. Depends on the transceiver that you're using, depends on the TOSA, depends on the lenses, and so on. But it's a very strong tendency that the longer wavelength couple to the center of the fiber. So now let me explain why this is important for transmission. And this slide combines what I'm talking about, the fiber and the laser. The laser here, coupled to the core of the fiber, and the DMD measurement that I'm talking about. Let me explain in this way. So from the chromatic properties, we know that longer wavelengths travel faster and shorter wavelength travel is slower. That's the properties of the chromatic properties of the glass, especially at that region, 50 nanometers, 900 nanometers, that happens. So if these longer wavelength coupled to the lower order modes that are slower in time than the higher order modes, you see fast light coupled to a slow mode, then you have a compensation. Now, on the other side, you couple the shorter wavelengths that travel fast. You have the shorter wavelength that travels slower to the higher order modes of the fiber and traveling faster. You have a compensation too. So this DMD tilt actually gets straight. So you have less difference between the speed of the modes after the coupling with this fiber, the one that tilts to the left. So you get like an equalizer, an optical equalizer in the fiber. Again, it's not perfect because this is a tendency. So there is a partial compensation of both of the modal and chromatic dispersion. However, the other fiber, the right tilted fiber, the opposite happens. Now the longer wavelengths that are faster coupled to the lower order modes that travel faster too. So this goes even faster. And the shorter wavelength that is slower coupled to the higher order modes goes slower and then goes even slower. So the slope even increased. So your dispersion, total dispersion increased, and your bandwidth decreased. Why is this important? Because during manufacture, you cannot control perfectly the fiber. So the same OM4 or OM3 can be less tilted. The same production can have some fibers being less tilted or right tilted with the same modal bandwidth measured based on standard. And then when we calculate reaches in the standard in fiber channel or IEEE, we always look for a worst case. So we need to look for this fiber. So that's the reason you might have noticed sometimes that there is high difference between the reaches that the standard publish and the ones you can get in your data center. It's because the fiber is slope. That's a main factor. It's not the only factor, of course, but it's the sign of the loss of the slope of the DMD has very important effects on the total bandwidth of the channel. Okay, so I hope I could describe the phenomenon for A50 nanometers, so why the DMD tilt is important for the A50 spectral window that is mostly used for communications on multimode fiber. But now we are using also solutions for BiDi or even SWDM, so we go to longer wavelengths. So in that case, also the DMD tilt sign has an impact, and I'm going to show that in the next slide. Here I'm showing modeling for left tilted multimode fiber and right tilted multimode fiber, how the DMD pulses will look at different points. And what I'm having in this curve is the effective modal bandwidth of the fiber based on this model. What's happening is that when you start changing the wavelength, the higher order mode start traveling slower than the lower order mode. So this DMD slope or curve, as you can see, start rotating clockwise in this direction. So as the wavelength start increasing, the DMD pulses become straight at some point. So imagine that this is the DMD pulse at this wavelength. As you start moving here, the fiber gets straight until it reaches a peak, a very high bandwidth. It can be tens of gigahertz per kilometer. It can be very, very high. It can be, in some cases, we have observed 30 gigahertz or very high bandwidth per kilometer. In this case, the fiber gets very straight. After that peak wavelength, it starts decreasing again, and it becomes right tilt DMD fiber. So all the fibers at longer wavelength become right tilted fiber. So, but the ones that they start like being left shifted fiber at 850 nanometers have significantly higher bandwidth at longer wavelengths because they start bending to the left, and because the rotation is clockwise, if you start moving here, let's say, certain number of nanometers, you end with a high bandwidth because you can see that start increasing. Whereas the one that they start like right tilted fiber start already bending in this direction. If you start rotating this clockwise, you can see that it gets worse and worse. This is the reason because left tilted fiber also perform significantly better a longer wavelength. They have more bandwidth. And I can show here some experiments trying to clarify that. We measure here in our laboratories many fibers at different wavelengths. We have a library of 400 or 480 fibers, and I'm showing just some of them to explain this concept. Ideally, at 850 nanometers, you would like to have maximum bandwidth, like this black fiber. In this case, this fiber has the maximum bandwidth at the 850. In reality, because of manufacturing variations, you get fiber like this one, the brown one that can pass the requirements for OM4 and E50, like 4,700 megahertz kilometers, and compare that with, let's say, the blue one that also can pass that. The blue one will be a less shifted fiber because the peak wavelength is higher than the E50 nanometers, whereas the brown will be a right shifted fiber because the peak wavelength is on the left, is below H50 nanometers. So now let's see what happens when you increase the wavelength. The brown one goes lower and lower in the total bandwidth, the effective nodal bandwidth, whereas the blue one is higher and higher until it reaches the peak and then it starts decreasing again. But for any value that you can see here, a longer wavelength, the blue one has significantly more bandwidth than the brown one. So this information can be used for modeling to estimate populations, and we have been used that a lot to contribute to standards, TIA fiber channel to estimate reaches. That's very important for developing of new solutions of a multimode fiber utilizing multiple wavelengths. Now I'm going to talk a little bit about the modeling and the results. I hope I have explained in previous slides the effect of the sign, the DMD sign, in the performance at 850 nanometers and also a longer wavelength. And now I'm going to talk a little bit about modeling. Again, we have used modeling for contributions to different standards. Basically, the idea of this is to estimate the worst-case bandwidth of the fibers so we can define the reaches that you can see in fiber channel or IEEE. In this case, the modeling I'm showing is using a known method called the Wenzel-Kramer bridge-in that is used for other physics applications too. And what we done here, we have a model 16,000 fibers from the refractive index. We have calculated the propagation constant and the mode group delays. And we have recreated the DMD pulses that you saw from measurement. And from there, we have computed the bandwidth distribution of the fiber that I'm showing here. Again, we have worked also for the H50 nanometers spectral window and also for other wavelengths. What is interesting here is, let's see, there are two populations here. One is the left multimode fiber, and this is for OM4, and the other one is the red one. That is the right-shifted, right DMD tilted multimode fiber. I try to create two populations that are quite similar at A50. As you start increasing the wavelength, the mode also tells you that the blue one start increasing. There are more fibers that have higher bandwidth because of this clockwise rotation of the DMD that I mentioned, whereas the red one start reducing the bandwidth. As you can see, at the 80 and 918, also the blue one has more fibers with higher bandwidth than the red one. The red one starts decreasing. And 953, what is the wavelength using the standard for OM5 for TIA, the red, the right system multimode fiber decreased significantly, whereas the OM4 left system multimode fiber still can have a bandwidth, significant bandwidth. We present this work and we collaborate with other companies to try to validate these results. We got good correlations with one important manufacturer of fibers, and the results are being used in the new IEC standard. The red one, for example, is the minimum bandwidth per wavelength published in the latest version of that standard, this red trace, you can see in all of them. the black trace, dotted trace, is the values for OM5 at different wavelengths in the TIA standard. And the blue dots and red dots are the results of modeling that I'm showing here for different confidence levels. Let me go to the correct slide. This one. So those are the confidence levels, 99, 97, and 95%. So for the standards, we use the red trace or the red dot, which represent the right shifted multimode fiber, and that represent a worst case for bandwidth. As you can see here, they can start with high value at 850, like 4700 for OM4, but they decrease very fast, as mentioned before. So, and reaching low values at 920 nanometers, for example. Whereas the less shifted OM4 have significant higher bandwidth. At some point, you can see here that for 95% of the cases, if you select properly the left shifted OM4, you can have similar bandwidth at the specified by OM5. So I think the main goal for us for this research was to try to understand the effect of the sign of the DMD field. And I hope I could explain that. I have explained that in this presentation. Again, there are two main effects. One is in the 850 nanometer spectral window that has been used for many, many years. And another one is a longer wavelength that we start use relatively recently, 3-4 years ago, for BiDi and SWDM. So the effect of bandwidth, again, is very important to develop new transceivers operating at higher data rates and using multiple wavelengths. In this case, this study focused in the region that is being proposed or now is being used for a 802.3 CM, that is for 400 gig multimode fiber solutions, that we're using wavelengths between 850 nanometers for one direction and 918 for the other direction. So basically, the results also indicate that the reaches has to be reduced because of the right shifted multimode fiber operation. That's the main limitation to extend the reaches. Using less shifted multimode fiber, you get significant higher bandwidth. Part of this work is going to support also the development of higher data rates like 100 gigabits per second per wavelength, as I mentioned before. Well, with this, I conclude my presentation. Thank you very much for listening, and let me know if there is any question.
And thank you, Jose. And at this time, we will ask as many questions from the attendees as time permits. I will start with this first question. Can this modeling technique be used to improve fiber manufacturing, real-time quality control, or is this more for data center installed performance?
I think it's for both. I mean, you can use the modeling to redesign the fibers to increase the population of less shifted multimode fibers. So with that, you get a significant gain on bandwidth, and in a statistical basis, you get a better population that will improve the reaches for a standard. Also, you can do, but it will be less likely, but you can, in the data center, you can create different specifications to only use fibers that have some negative sign in DMD tilt. Then you get higher bandwidth for your channels too.
Okay, thank you. Next question. What types of fiber design parameters help to achieve more ideal tilts to improve channel bandwidth?
Basically, the refractive index profile is key. The design of the refractive index profile will allow to increase the tilt of the DMD profile in such a way that you can increase your population of less tilted fibers during production. Because during production, there are always manufacturing variations, so you cannot maintain exactly the same profile. But if you bias a little bit the refractive index profile, you can increase your population of left tilted multimode fiber and reduce the population of right tilted multimode fiber.
Okay, thank you. Next, are there any other wavelengths worth measuring for OM4 or OM5 performance other than bidirectional 850 nanometers and 918 nanometers?
Yeah, there are wavelengths for SWM. We use like 940 nanometers. However, one of the advantages using the BiDi with these two wavelengths, 850 and 918, is that they are more compatible with fibers already installed in data centers. Because as I mentioned before, if you start increasing the wavelength, the bandwidth decreases very fast, especially for the right tilted multimode fiber. So if you use very long wavelength, basically you need to replace your fiber that is right tilted, because it's not going to provide the sufficient bandwidth. The good advantage of BiDi operating at longer wavelength, but not too long, like 920, 918, or 910, is that you still can reuse the fibers that you have already installed, especially if the reaches are not too long. So that's the reason we see some advantage in using multiple wavelengths, but not going so far in the spectrum like 940 or 950.
Okay, thank you, Jose. I don't see any further questions at this point. So I would like to thank you, Jose, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Jose after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, February 21st at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 68 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next 69th Annual International Conference will take place on Sunday, October 11th through Wednesday, October 14th, 2020, at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, the 4th Annual UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 24th through Thursday, March 26th, 2020, at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.